The left and the right are both doing quicksort. They started at the same time and on the same set of data. The only difference is in how they chose the pivots. And the right side is done. The left side chooses awful pivots, making quicksort catastrophically slow. But for this other data, the way I chose pivots on the right is basically just as bad. Is it possible to choose pivots in a way that guarantees we never suffer a horrible slowdown? Let's first be clear on the nature of the problem. Quicksort works by choosing a pivot and partitioning. As we start partitioning, we swap the pivot to the right side, then there's a lot more swapping and comparing. The partition finishes with everything smaller than the pivot on the left and larger on the right. We then quicksort each side. A good pivot is fast to choose and cuts the problem roughly in half, so that when we quicksort each side and partition them, we have a lot less work to do. The worst possible pivot is something more like this. Here, it's the largest item, or it could be the smallest. After the partition, we end up with nothing on one side. So when we make this recursive call, there's almost the same amount of work to do. If we always choose bad pivots, we end up with a horrible slowdown. Specifically, the worst case will be quadratic runtime, O of n squared, whereas we'd like our quicksort to always be O of n log n. And the difference between O of n log n and O of n squared can be the difference between seconds and days. So is it possible to ensure we avoid this and get this? Let's get some bad methods of choosing pivots out of the way first. As you've probably realized by now, using the first element as pivot can be bad. With a reverse sorted array, like what was on the left at the video start, we repeatedly use either the largest or smallest item as pivot, resulting in unacceptably slow quadratic runtime. If we choose the last item instead, we end up with the same problem. And the same idea applies when choosing first or last in an array that's already sorted. Sorting something that's already sorted is actually quite common, so blindly choosing the first or last item as pivot isn't a great idea. How about choosing the middle? That's what we had at the video start on the right. For the common case of already sorted input, this avoids a quadratic slowdown. But consider this case. When I choose the middle as pivot, it's the largest item. So when I call partition the second time, I've only reduced the size I have to partition by 1 or 2. And it'll be the same for the third partition, the fourth, and so on. I still get quadratic runtime, and we can't have that. Now, is an input like this something we actually need to worry about? Well, it's not as common as an already sorted array, so choosing the middle element as pivot is an improvement. But this input array isn't that contrived. It's just a sorted array glued to the same array in reverse. So choosing the middle is not bad, but it can't guarantee we'll never have a slowdown. Another option for choosing the pivot is to take the median of 3 items, often the first, middle, and last. But does this guarantee we'll never get bombed by quadratic runtime? No. An academic paper linked in the description lays out how to construct an array to beat this. But at least for the simple quicksort I'm using in this video, a decrease then increase causes it to bog down. So we're still looking for a foolproof way to choose pivots. How about we take the median of 3 medians of 3? Sounds confusing, it's really not. This technique is called pseudo-median of 9, or the ninether. We'll take 9 evenly spaced elements, and do median of 3 for the first 3 of those 9, the middle 3, and the last 3. Then take the median of those, and partition around that item. This handles the decreasing then increasing array easily. Using the pseudo-median of 9 as pivot is most suitable for larger arrays, since the cost of getting so many medians may not justify itself for small ones. I'm showing pseudo-median of 9 here for everything bigger than 9 items, but really you might want 40 or 100 or more to use this. Now, is it possible to construct an input that causes a quadratic slowdown here? Maybe. It seems like it would be, but I didn't find anything concrete on how to do that. Let me know in the comments if you know. So pseudo-median of 9 looks like a winner. And here's another winning pivot choice that's simpler. How about we pick a random pivot every time? It's very easy to do this. Just generate a random number within the proper range and use that as an index for the pivot. This will avoid the pitfalls we saw when choosing first, last, or middle. Or you could just shuffle everything before you start and use the last index or the first or whatever. Both of these ways of randomizing work well for choosing pivots, because it's extremely unlikely, in practice, for a random pivot choice to get quadratic runtime. You'd have to randomly select a horrible pivot every time, and on a bigger array, that's unlikely enough to be almost impossible. But doesn't this almost bother you? can't we make quadratic runtime on Quicksort actually impossible? In theory, yes. So what if we just make sure we have the perfect pivot every time? Which element would that be? The median. Using the median's pivot gets half the elements on one side and half on the other every single time. For us to get O of n log n worst case for Quicksort, though, we have to find the median in linear time. The commonly known quick-select algorithm can find the median in linear time for the average case, but it's O of n squared worst case. However, there's another algorithm, seldom seen outside of textbooks and classes, that always finds medians in linear time. It's pretty tricky though, so we'll skip the details. What you may be wondering is, if it's possible to find the median in linear time every time, why doesn't everybody just do that? Because the linear time selection algorithm is rather complex and it needs 2 recursive calls. And that's inside of Quicksort, which itself is making recursive calls. So theoretically, using the special algorithm to choose the median as pivot gives O of n log n time for the worst case. But in practice, it's too complex and bogs down. Simpler ways to choose the pivot perform better. So the answer to the question we started with is pretty much yes in practice, and yes in theory, but not in both in the same way. So what do you use if you're coding up Quicksort for yourself? Random pivots are an easy and generally good solution, and it's also common to choose pivots in different ways for different sizes, such as using pseudo-median of 9 for large partitions and switching to simpler methods as the partitions get smaller, eventually using insertion sort for subarrays below a certain size. If you'd like to see a video on that and on other Quicksort optimizations, let me know in the comments, and I'd really appreciate your feedback for what I could improve in these videos as well. I'm Coach Slate. Thank you for watching.